Hello, my name is Rob Reynolds. Welcome to College Algebra Section 6.5. I actually did 6.4 on another video, but today I'm going to start on Section 6.4 very quickly, review how to graph logs and what the definition of a log is. But the majority of this video is going to be talking about the log properties, and I'm going to try in the same video, I don't know if I can do it in 15 minutes, we're going to talk a little bit about solving logarithmic functions. To undo a log function, we're going to use exponents, just like addition undoes subtraction and multiplication undoes division. To undo an exponent, you need the definition of, and the definition of a log is right here, converting it to an exponent. I kind of like this. If you ever see a log function, I would set it equal to y and do and then do this fishhook, or the definition b to the y equals x. So again, we're changing logs into exponents. So there's the definition of logs. Then we learned how to graph logs. We learned that they are the inverses of exponents. So here's an exponential function. Exponents start at 0, 1, where logs start at 1, 0. And on section 6.4, we looked at the domain and the range of, remember, they're inverses. So the domain of the exponent becomes the range of the log, and vice versa. So here's what the log function looks like, where it has an asymptote at x equals c, in this case at x equals 0. This one is shifted 2 units to the right, so the asymptote would be at x equals 2. So again, my previous video, we talked about how to graph using the definition. In this video, I'm going to be talking about, well, here are some properties. These are not the 3 main log properties, but these are some good log properties that keep creeping up from time to time. And it says the log of 1, no matter what the base is, even if it's base 7, is always equal to 0. And that's why the graph goes through the point 1, 0. Of course, unless we have a negative x, then you start at negative 1. But again, watch section 6.4 for the graphing for that. Whenever the base is equal to the argument, such as the log of 5, base 5, that's also equal to 1. And you can see why, because if you do the definition, 5 to the first will equal 5. And this is another property of logs, where you can bring the x down up front. All of this in yellow is equal to 1. So if you bring the x down up front, it's x times 1 because of the previous definition, and of course that's just x. And then the last one says the log of this is equal to the log of that when this equals that. So it's kind of like unlogging both sides. You can do whatever you want to both sides of the equation. So if you just drop the log of both sides, you get a nice little definition. And those properties work not only for logs, but they also work for natural logs. Remember, the log of x is equal to the log of x base 10. There's an imaginary 10 there, but unless I use the natural log, if I don't write the natural log base, then we assume that it's base e. And then you can look at my section 6.4. Here's the exercise that I went through, and I graphed not all of these, but I think several of these, to try to talk to you about the growth and the decay. There are 3 things that cause decay, which are the same 3 things that cause decay for exponents, which is a negative x, a negative a, and a b value between 0 and 1. Your asymptote is always at y equals c. Be careful for exponents, it's at y equals d. And then the start value was either at positive x. So if x is positive, we start at 1, 0, and if x is negative, we start at negative 1, 0, because you can't take the log of a negative number. So for this example, see how the log, the x value is negative, so I would put an open dot at negative 1. This actually is going to go 5 units to the right, because when you set that parentheses equal to 0, 5 minus x is equal to 0 when x is 5. And this is going to go 3 down. So I would take this open dot and count 1, 2, 3, 4, 5 right, and 3 down. There's, I know, a point on my function. Another point on the function, which is not hard to find, is if you let x be 5, all of this in yellow will go to, no, let's do this. Yeah, 5's not bad either, but this is even better. If you let x be 0, that's interesting, because then we'll get the log of 5 base 5, which we know all of that yellow is 1. So if you let x be 0, then we'll get all of that yellow to be 1, and 1 minus 3 is negative 2. So I just found another point, 0, negative 2. The asymptote's also at x equals 5, so 1, 2, 3, 4, 5. And let's see, the decaying factors, I've got a negative x, but that's it. So I just have one decaying factor, and therefore I'm going to have decay. If I had two decaying factors, it would be, so the graph would probably look something like this. And remember, it's much, it doesn't matter for me if you graph it up here, but see that other point that we found really helps define, oops, 0, -2, I kind of missed it. That other point really kind of helps. It's very, very, very flat, because remember, the log of 10, you're only out at 1, and the log of 100, you're only up 2. So these things are much flatter than what you think. But if you were to draw the red, that's a good decaying function, but to get a little bit more accurate, you could always find this property, the log of 5 base 5 is equal to 1. You could always look for that. So you can see I totally missed it. Again, the graph would be a heck of a lot more accurate in green than it is in blue, but I'm just looking for general shapes. I'm looking for a point, an asymptote, and then either growth or decay. So you can go through and look at the graphs of these in section 6.4, but again, this video, I've already spent 6 minutes talking about 6.4. I really want to talk to you about the properties. And there are 3 log properties. I've already given you some log properties, but here are the product, the quotient, and the power properties. It says the log of AB is equal to so if you multiply two numbers together, so for example, if you have the log of 6 times 4, that's the same thing as the log of 6 plus the log of 4. You can actually type in the log of 24 into your calculator and find out this decimal, the log of 24, should equal this sum, the log of 6 plus the log of 4, and that's the first property. So if you multiply, you add. If you divide, you subtract the logs, and the last property is this power property. You can bring that n down out front and make it n times the log. By the way, all those properties also work for natural logs as well, just the base changes. So looking at these log properties, find the exact value of each expression. I would set the log equal to y and fishhook, because we want to undo the log. So I'm calling this the fishhook, which is the definition. So I would say 5 to the y is equal to, did you know that the cube root of 5 can be written in exponential form as 5 to the 1/3? Simply because the square root of x is x to the 1/2, and of course we have all these invisible numbers here. There's a little 2 here that I don't have to write, there's a little 1 there I don't have to write, and if I didn't write this little base 5, we would assume that to be 10. In fact, here's an invisible number. A little base e is sitting down here even though I didn't write it. How do I know that? Because if you don't write the base for a natural log, it's base e. And then this is kind of a neat rule. If 5 is equal to 5, then I know that these exponents are going to be equal. So all I have to say is y equals 1/3, and I'm done for that problem. For this one, I can see the log of, let's let this blue guy be a, and let this pink guy be b. So this, when I see this, I see the log of a minus the log of b. And the log of a minus the log of b is the log of a divided by b, which I know if I divide exponents, I rewrite the base and subtract, so it's e to the 4th. I can bring this down out front. That's 4 times the natural log of e. And again, perhaps you remember, whenever the base is equal to the argument, that's equal to 1. So this is just 4 times 1, or 4. Yes, you could do this on your calculator, but the point is, I'm not trying to train you to be a monkey. I want to make sure that you understand these properties and can actually use your brain to actually solve for these. Now this is interesting. This is an expand. That's when you can't do on your calculator, so you have to use your properties. This actually says the log of a times b times c, which I haven't talked to you about, but it's really just the log of a plus the log of b plus the log of c. And don't forget, you're not done, because we can expand this just a little bit further by using that third property, the power property of logs, and make this the log of 5 plus 3 log x plus the log of y. This one's kind of interesting. I'm going to rewrite this to be the natural log of 3x minus 5 to the 1/2. So you can see I'm going to eventually bring that 1/2 down up front. But before I do that, this actually says the log of a in yellow divided by the log of b. So I'm going to take care of this quotient property first, which is the natural log of a minus the natural log of b. So remember, the natural log of a divided by b, a is the yellow, all of that in yellow divided by blue. So that's the second property, the quotient property. Then I can bring that 1/2 down up front. So 1/2 the natural log of 3x minus 5 minus the natural log of 7. And remember, this 1/2 does not apply to this, so I wouldn't put parentheses anywhere because I don't want to distribute the 1/2. That's pretty much expanded. Be careful. Sometimes students try to do something here, but the natural log of a plus b, I want you to remember, is absolutely nothing. You cannot change this to the natural log of 3x minus the natural log of 5. That's nothing. You better quit while you're ahead. So now let's go the opposite direction. Let's condense. Let's put things together. So if this has already been dropped down up front, let's put that back up top to make that the log of x to the 1/2. And let's do the same thing with the 3. Throw the 3 up top. So plus the log of x plus 1 cubed. Now I see the log of a plus the log of b. So I'm going to rewrite the log of a plus the log of b is the log of a times b. X to the 1/2 times x plus 1 cubed. Ooh. I don't have like bases. I would probably leave this. This is nasty and disgusting. I think that would be my final answer. You could go further, but it's going to get bad fast. So I'm going to quit right there. Part B, I would take the 2, throw it back up top. So remember, if it's pulled apart, we put it together. If it's together, we pull it apart. You just keep doing the properties forwards and backwards until you have this thing condensed. So we're trying to make this into just a single logarithm like we did over here. Even though this didn't look very nice, it's a single log. So this could be a single log because I see, once again, the log of a minus the log of b. Oh, over here I have the plus, so I multiplied. Over here I have a minus, so I'm going to divide the natural log of x plus 2 squared divided by x. And again, I would probably quit. That's condensed. I would stop. You can try the third example. This is interesting. This says, hey, if you have 3/5 and divide by 4, do you recognize that as 3 over 5 times 4? I want you to, because when you divide by 5 and then divide by 4 again, that's like dividing by the product. So 3 is being divided by 5, and then 3 is also being divided by 4. You can check that on your calculator. 3/5 divided by 4 is the same thing as 3/5 times the reciprocal, which is 1/4. Maybe that's easier for you to see, but that is equivalent. So when you divide and divide again, it's like multiplying the two things you're dividing. So that's what's happening over here. You've got the ln of x divided by x plus 1, and then that whole thing is being divided by x minus 1. Well, that's the same thing. Again, you're dividing and dividing. That's the same thing as the ln of x over x plus 1 times x minus 1, which is really, I can simplify it. The natural log of x, if I FOIL this together, first outer inner last, I see the conjugate, so the outer and the inner will cancel, leaving me with x squared minus 1. That's pretty simplified right there. Remember, you cannot cancel part of a sum. That will tick me off, so that's the POAS, part of the sum. Don't cancel like that. You can't cancel x's there. So I would leave it. Final answer. Change of base. So we have the definition. You've got 3 log properties, the product, the quotient, and the power. And then we have this nice change of base. What's the purpose of the change of base? Well, you can't type in base 4 into your calculators unless you use the change of base, which says the log of 25 divided by the log of 4. Now I want to be careful. I want you to be very careful. This does not equal the log of 25 minus the log of 4, which remember was the log of 25/4. So students generally get that mixed up. The purple does not equal the red. This is property number 2, which looks similar to the change of base, but it is different. So I just want to give you a heads up. Students struggle with this. Notice this has a single log and you're going to 2 logs. This has 2 logs and you're going to a single log. So be careful. You never take a single log and move to a single log, and you can't take 2 logs and write it as 2 logs. So if it's single, it goes to double. If it's double, it goes to single. That might be helpful. So here's all the things that we reviewed in this video. We got the definition, this fishhook, a to the y equals x. We've got the 3 log properties, the product, the quotient, and then the power rule. Remember, you just bring that r down up front. And then I have a change of base. And these are your properties, and this is a rule or a formula, and this is a definition. So a bunch of, and then here's a quick little review. If you're interested, I'm going to try I'll post 6.6 on a separate video because I'm at my 15 minutes already, and I don't know, you guys get tired of me talking, so email me.